Welcome to Excel 2013 Statistical Analysis video number 61. Hey, if you want to download this workbook, Business 210 Chapter 9, second file, click on the link below the video. And this is our last video for Chapter 9. We got to do hypothesis testing for a proportion. Here's our question. The school newspaper stated that the proportion of students who knew when the presidential election would be held was 15%. Our researcher thought that this was low and wanted to show that the proportion of students who knew when the presidential election would be held is higher than 15%. The researcher took a random sample and made sure he got respondents from all of the different demographics, including night students, online students, new immigrants, and others. At alpha 0.01, can the researcher conclude that more than 15% of the students know when the presidential election will be held? Now, one thing the researcher probably did is they thought, well, this seems really low. Maybe they made an error when they sampled. The population being sampled maybe didn't include some of the groups. So when the researcher went out, they made sure to try and get all of the different, do a true random sample that really sampled the actual population at this school. Now, the thing about proportions is we've got to check if it's binomial. And we've done all of the calculations we're going to do here in earlier chapters when we did proportions. We have to check whether or not this is a binomial test. Is fixed number of trials? Yes. We'll see there's exactly, we asked 152 students. Probability stays the same each time? Yes. Yes or no. Trials are independent? We'll assume that they are. Each trial results in a success or a not success? Yes. Well, what is a success going to be for us? It's going to be answering, yes, I do know. Not success will be, they don't know. All right, and so we have these 4 tests, but then there's 5, 6. You have to make sure that n times p is greater than or equal to 5 and n times 1 minus p. So I went ahead and already calculated these. And in both cases, they were greater than 5. Here's our hypothesized population proportion, 0.15. Now, before we set up our test, let me scroll down here. We got to look at the point of view and the goal. The point of view is a researcher who is skeptical of a reported proportion of the number of students who knew when the presidential election was. So that's our point of view. Our goal, test to see if there's significantly more than 15% of the students who knew when the presidential election would be held. So we're looking, again, significance. That means we have to pass that hurdle before we reject the null and accept the alternative. The more than 15%, that phrasing or that thinking of what we're doing here helps us set up the null and alternative hypothesis. So I'm going to come right down to the alternative because this is more. This is, notice we do our little symbol, right? And that means it's pointing, that little small side's pointing towards the upper or right side. So this is a test on the upper side. So I'm immediately going to come here. We do the same thing, except for instead of mu, we use p. So is the proportion greater than 15%? Remember, once we know the alternative, we go up to the null hypothesis and flip it. Less than or equal to the equal sign always goes with the null hypothesis. All right, our alpha is going to be 0.01. We want to be super sure here. We want to set the hurdle high. Remember, if the alpha is low, then the hurdle is high. Type 1 error is reduced when we increase alpha, which means we have less of a chance of rejecting the null hypothesis even though it was true. All right, now we need to come up and make some calculations from our sample. We have, OK, so we have a sample, yes or no, knew when the election was. I'm going to count the yeses and the nos. So yes, we're going to use the function COUNTIF. Count not everything, but count if some condition is met. So the range, I'm going to click in that top cell, Control-Shift down arrow, and F4 to lock it, comma. And I've set up my criteria yes and then no on top of each other. So I'm going to click there as a relative cell reference. Control-Enter. And then when I copy it down, it got the right null. So we have 36 and 116. Now, this is our total. And now we can calculate our probability. By the way, this should look familiar. This is what we did in Chapter 2 when we did relative frequency, right? So I'm going to say the part divided by the whole, F4 on the 152. So we have a probability yes of about 2.4 and about 0.76. All right, now we can go ahead and here's our sample proportion, or P bar, right? So we come down here. We have step 1, step 2, step 3. We have our 0.2368. That'll be our P bar. We have to calculate standard error. And the formula is page 28 in the PDFs, but here it is right here. We've done this in earlier chapters. Square root, and we're going to take our, actually want to go up and get it from our source, our place right here. I guess one more. So it's P times 1 minus, and then divide by n. And the order of operations will work fine there. They're all left to right, so close parentheses. And our standard error is going to be 0.0289. Now we can calculate our test statistic, right? Whatever our statistic is minus the hypothesized parameter divided by the standard error. So we say in parentheses, let me go down just a little bit. There's our P bar minus our hypothesized proportion up there, close parentheses, divided by our standard error. Wow, so we got 2.9. Now, the distribution we use for proportion is the z distribution. So that's 2.9, almost 3 standard deviations above. You can already guess. I mean, this is the 7th or 8th test we've done in this chapter. That's way above, 3 standard deviations above. So we're probably rejecting the null and accepting the alternative. Let's go ahead and calculate our p-value. Now, if we calculate a p from this is on the upper end, and we want the probability above it. So we have to do 1 minus. And back to our norm dot. So I need my S for the standardized normal distribution. So there I have my z, comma 1 cumulative. It will calculate all the way up to this, which is a lot, and then 1 minus that will give us our probability. So this value here is amazingly small, which means it gives us very strong evidence that we should reject the null and accept the alternative. We compare it directly up to here, and obviously much smaller. Our critical value rule, we're going to use the inverse. So norm.s.inverse. And our probability, well, we're on the upper end, so we need to say 1 minus our alpha. Our critical value is 2.32. So comparing that, anytime our test statistic is greater than or equal to this, we reject the null and accept the alternative. So either way you go, we come to the same conclusion as we said many times so far. Our conclusion, because the p of approximately 0.0014 is less than or equal to our alpha, we reject the null and accept the alternative. If we're using our critical value rule, because the test statistic 2.99, almost, it's 3 standard deviations in essence, is greater than or equal to the critical value of 2.33, we reject the null and accept the alternative. There is strong statistical evidence to support the claim that more than 15% of the students know when the presidential election will be held. Said a different way, at alpha of 0.01, our sample proportion of about 0.24 provides very strong statistical evidence to suggest that more than 15% of the students know when the presidential election will be held. And finally, we do run a 1% type 1 error risk of saying that more than 15% of the students know when the election will be, when in fact they do not know. Now again, once you get a p-value like this is very strong evidence. All right, that's hypothesis testing for a proportion. We've done a lot in Chapter 9. We'll see you next video.